In physics, symmetry refers to a fundamental property of a physical system or law of nature that remains unchanged under a specific transformation. This concept is a cornerstone of modern physics, providing deep insights into the fundamental laws of the universe and their associated conservation laws. At its core, a symmetry implies that if you perform a certain operation on a system, the system's essential characteristics or the physical laws governing it will appear identical. This is not just about the geometric appearance of an object, like the symmetry of a snowflake, but extends to the very fabric of physical reality. The profound connection. Noether's theorem, formulated by the mathematician M. E. Noether in 1915, establishes a profound and direct link between a continuous symmetry of a physical system and a corresponding conserved quantity. This theorem is a central pillar of theoretical physics. Here's a breakdown of the key relationships. For instance, the fact that the laws of physics are the same today as they were yesterday, time translation symmetry, is the fundamental reason why energy is conserved. Similarly, the observation that the laws of physics are the same here as they are in a distant galaxy, space translation symmetry, leads to the conservation of linear momentum. Types of symmetries in physics. Symmetries in physics can be broadly categorized into several types. Continuous versus discrete symmetry. Continuous symmetries. These involve transformations that can be changed by any arbitrary amount. A classic example is the rotation of a perfect circle. It looks the same after being rotated by any angle. The symmetries linked to conservation laws by Noether's theorem are continuous. Discrete symmetries. These involve transformations that are distinct and non-continuous. A square, for example, has discrete rotational symmetry because it only looks the same after rotations of 90, 180, 270, and 360 degrees. Important discrete symmetries in particle physics include charge conjugation, C, swapping a particle with its antiparticle. Parity, P, reflecting a system in a mirror. Time reversal, T, running a physical process backward in time. For a long time, it was believed that the laws of physics were invariant under C, P, and T transformations individually. However, experiments in the mid-20th century showed that the weak nuclear force violates C and P symmetry. While the combined C-P symmetry was also found to be slightly violated, the combined C-P-T symmetry is believed to be a fundamental symmetry of the universe, meaning that physical laws are unchanged if you swap particles for antiparticles, take the mirror image, and reverse the direction of time. Spacetime versus internal symmetry. Spacetime symmetries. These relate to transformations in space and time, such as translations, rotations, and boosts, changes in velocity. The principles of special and general relativity are built upon fundamental spacetime symmetries. Internal symmetries. These symmetries do not act on spacetime coordinates but on the intrinsic properties of particles themselves, such as their charge or flavor. These are described by abstract mathematical groups and are crucial to the standard model of particle physics. Global versus local symmetries. Global symmetries. The transformation is applied uniformly across all of spacetime. For example, if you change the phase of all electrons in the universe by the same amount, the laws of electromagnetism remain the same. Local symmetries, gauge symmetries. The transformation can be different at each point in spacetime. These are more powerful and form the basis of our modern understanding of fundamental forces. For example, the theory of electromagnetism is a consequence of a local gauge symmetry. The importance of broken symmetry. While symmetries are fundamental, the instances where symmetries are broken are equally important. Symmetry breaking occurs when the fundamental laws possess a symmetry, but the outcome of a physical process or the ground state of a system does not. For example, a pencil balanced perfectly on its tip has cylindrical symmetry. However, when it falls, it chooses a specific direction, breaking that symmetry. In particle physics, the concept of spontaneous symmetry breaking is crucial for explaining phenomena such as the origin of mass for fundamental particles through the Higgs mechanism.